Okay, so here's one of the animations I kept forgetting about. So can you tell can you see green, red, and blue vectors there? Can you distinguish those colors? People in the front are saying yes, people in the back are saying no. Maybe when it starts you'll be able to see better. But so which one is T, which one is N, and which one is B? Here we go. Which one's T, which one is N, and which one is B? Let's go slower than that. Which is T, which is N, and which is B. Maybe we'll tell here. This will help. So, which is T? Red. Which is N? What's N? Green. And then blue. That's the final.
Just say the light color.
So the one pointing down now is T. The one pointing up now is N. And then the one pointing kind of to the right and back, that's B right now. Okay, so what's cool about this video is then they give you, like, as if you're on a roller coaster. And so if you're on the roller coaster, you're looking straight out, and what vector is that you're looking straight out? T. Okay? So this is cool because they add the osculating circle in here. Let's go back to normal speed. So now they're going to add the osculating circle, and that's in the plane. So the osculating circle is the plane of which two vectors? Which two vectors are parallel to the osculating plane? T and N, right? T and N are the plane of the curve, therefore they're the plane of the osculating circle. Okay, now you're gonna be looking out at the T vector always. So you always have the view of straight out the T vector like a roller coaster. So the gold, you can kind of see the gold is the osculating circle, and the black is the actual curve. So what they don't do is they always have the direction of turning straight up. So that would be nice if it didn't do that, but that's just a little review. Okay, so then this is the other thing I wanted to show you. And so we have something like a bouncing ball here, but there's something else running. Hold on a sec. Stop. Go away. Okay. I don't know why it's having trouble there. I don't know, something else is running, but it's kind of. But anyway, at the top is at the very top, when the ball is at the top of its path here, is the speed constant or changing? Or sorry, is the speed, what is the speed like at the very top? Right now. Speed is 0, right? Speed is 0. What about the acceleration at the very top? Is that 0 or is that positive or negative? So is there some non-zero acceleration when it hits the top? Right, because it's slowing down on the way up, right? And then speeding up on the way down. So that means it's constantly accelerating downward for that whole, when the ball is towards the top of its path, it's accelerating downward, slowing down on the way up, speeding up on the way down. So that means it has at the top, it has changing speed or constant speed? It has downward acceleration at the top. Does it have changing speed or constant speed? Changing speed, right? Okay, what if I told you it has constant speed? How would that be possible? Is it accelerating downward? Yes, it's accelerating downward. Does it have constant speed or changing speed at the top? Is it accelerating downward at the top? Okay, so who's learned something about acceleration? Is it accelerating downward at the top? Why? That ball is traveling at a constant speed at the top, but it is accelerating downward. Why is it accelerating downward? That's the turning part of acceleration, right? There's two parts of acceleration. There's speeding up and slowing down, which looks like it is because something else is running. That's frustrating. I want a nice smooth path. What else is running here? No. That's what's running. Okay. So much better. Okay. So that ball is traveling at a constant speed, but it is accelerating downward. I'll stop at the right moment. Oh, almost. Okay, it's accelerating downward at the top. But that acceleration downward at the top is not due to changing speed. It's strictly due to the turning acceleration. So what you were seeing as a changing speed before and concluded that it's accelerating downward was the change in speed due to turning, right? The actual speed of the ball is not changing, but it is changing speed at the top due to turning. So this has a 0 AT acceleration, and then some non-zero acceleration at AN, right? Okay, so that just shows that when things turn, they accelerate, and that's what you're seeing. That's what you're seeing in this view. You're seeing acceleration due to turning, and that thing is actually traveling at a constant speed. Okay. Yes, please.
Constant acceleration.
Magnitude, but constantly changing in direction.
Okay.
So yeah, so constant. The acceleration due to turning is constant in magnitude, but constantly changing in direction because n is always pointing to the middle of the circle.
Okay.
So yeah, so the magnitude of that angular acceleration stays constant. But as soon as it moves a little bit, the direction of it changes.
So A and N is always changing.
The direction. The direction is changing. But the magnitude of it is staying the same. Non-zero. Okay. So that helps. All right, and to remind you, the written work due Wednesday is longer. There's a 2-page acceleration activity that you did not look at in recitation, in addition to the recitation problems. So you should have started by now. If you haven't, don't wait till tomorrow. Start tonight, okay? It's longer. And that 2-page acceleration activity is very important. It kind of brings together these concepts of the tangential, the normal vector, and the tangential and normal components of acceleration, and how that all put together gives you the second derivative of the vector function. So it's like it's guiding you along to help you understand things along the way. So don't just try to get the right answers. So listen to how it's calling you to understand things, okay, as you're working it. And then retain that for the exam. Okay. Where are we at? We're talking about partial derivatives. Not that. That's I want vectors copy. This. There you go. Not that. This. Okay. So we were talking about partial derivatives. So if I have a function down here at the bottom, if I have a function f is equals f of xy, I want to practice this, interpret the meaning of the partial, if the partial of x when x is 4 and y is 7 equals to 5, and the partial of y when x is negative 3 and y is 8 is negative 0.5. You're going to practice what does this mean, right? So this is a mouthful. It's a long explanation to explain what these things mean, and we want to practice that and really understand it. Get a partner. Everybody's practicing. Everybody has a partner. If you don't have a partner, Jennifer will find you, and you're going to practice with Jennifer. Okay? Go. What do all these symbols mean? Partial derivative. Okay. Taylor, what do you think? Okay, so say it in your own words. So we're practicing saying it.
So I'm saying that it's 5 times the change in z with respect to x at point 4.
5 times the change in z with respect to x. Okay, so we got some of the words right, but we got to put it together. Nick knows. Key, what about you?
Well, said like when x is equal to 4 and y equal to 7.
Okay, good start. When x is equal to 4 and y is equal to 7.
Any change in z changes x 5 times that change?
Other way around. What are we going to do? So we're gonna mess with the independent variable, right? And then we're going to see what happens to the dependent variable. So when x is 4 and y is 7, what are we going to do first? Yeah.
Find the rate of change for annually y the x value.
Okay, and what is it? You said you wanted to find it. What is it? What is the rate of change?
The rate of change for the x value should be 5.
Okay, the rate of change is 5, and what does that mean that the rate of change of z with respect to x is 5? What does that mean? Samuel, you want to try?
I said for every, continuing on from what we had built up, I said for every, I think for every change in z, x changes by 5.
For every change in z, x changes by 5. Is that right? Samantha, you want to try?
The change in z is 5 times the change in x.
There we go. Okay, so yeah, so the change in z is 5 times the change in x. So when x is 4 and y is 7, what are we going to mess with? What are we going to tinker with? No x, right? If this is the partial with respect to x, then y is held constant, right? We're holding y constant at 7, and we're going to let what? X change a little bit, right? We're saying given. So this may be the key word to get us started. Given, right? Given what? Given a small variation in x. That's how rate of change works. You vary your independent variable a little bit, whatever that is. So holding y constant at 7, given a small variation in x around 4, what do we know?
Z changes by 5 times.
Z will vary by 5 times as much as that variation in x, or the change in z is 5 times whatever the change in x is. So what is z doing as x increases then, first of all? So what is z doing? Z is it increasing or decreasing? Increasing because? Positive, right? So as x increases, we see z is increasing because the rate of change is positive. And how is z changing? A lot or a little? It's all relative, but it's changing 5 times as fast as however x is changing, right? So for a change in x, z is going to shoot up 5 times that amount. So maybe that is fast in context compared to 1 to 1, but maybe that's slow in another context, right? But basically, z increases at a rate 5 times x, or the change in z is 5 times the change in x, holding y constant at 7. Okay, let's try this one. Somebody new. Yeah, Emily.
At point -3,
Okay.
z changes -0.5 times as fast as y.
Good. Okay. Yeah. So at the point -3, 8, what are we holding constant? We're going to hold x constant at -3. We're going to let y change a little bit, and this tells us that z will change by -1/2 times as much as the change in y. So what can we say about what's happening here? What is this telling us about z for changes in y? Decrease, right? So decrease, right? So for a change in y, we see a decrease in z. And then how much change? A lot or a little? Yeah, so like half as much. However much y changes, z is going to change half as much and decrease, right? Decrease half as much as y increased. Okay, we're going to keep practicing that. That's really important so that we understand the meaning of rate of change, right? The meaning of rate of change. Given a change in your independent, now you have to figure out which independent it is, because there's more than one independent variable. But given a change in your independent, the rate of change tells you that your dependent variable is going to change by a multiplication factor of that compared to the change in your independent that you picked. Keep practicing talking it out. And it's not, and the point is to like get to understanding of it, not just trying to remember the words that I'm saying and then try to like retell the words that I'm saying. It's about understanding it so you can just say it in your own words, okay? That's the goal. All right, so we were talking about looking at these partial derivatives in the different representations of, what were the different representations of? So we have function definition, that's using your derivative rules, right? Derivative rules from Calc 1, where you hold the other variable constant and you use the power rule and the chain rule and the quotient rule, etc. Surface in R3, we looked at that briefly at the end. So let's look at that again. So I have, remember the guitar string function, okay? So remember the guitar string function? There's that function. And remember what x was? X was just no, as a quantity, what did it mean? Yeah, so just no, that's not x. What was x? Distance down the string from the end. Shouldn't say down. Distance from the end of the string. And that was in millimeters. Right? And then y was, remember what that was? Time since we plucked the string in milliseconds. And then our value, our dependent variable z was, or f of x, y was, that was displacement, up or down displacement, right? Up or down displacement. Of the string. At that particular distance x, and at that time in milliseconds. Okay, so I have a cool kind of thing here. This. Let's try light blue. So what am I holding constant there? What am I holding constant, and what am I changing? So what does that plane, a particular plane represent? Let's see. So that tealish plane, that bluish green plane, represents one value of what? X, Y, or Z? Those are multiple choice. Y. So each one of those planes is Y. What was that again? A time, right? So by moving that plane, what am I kind of revealing there? What am I showing? By moving that plane, increasing Y. If I let Y increase, what variable am I letting increase? What quantity? Time, right? So this is like time going by, right? And at any particular time, what do you see on that graph?
Function of z and x.
What's that?
A function of z and x.
Function of z and x. And what was x again? Distance down the string. So it's like the string, it's the distance down the string is coming out at us, the x coordinate. And then the z coordinate is? Okay. So why is this a super cool animation then? What are you seeing there? You see what you're seeing? Anyone see what this is showing? What is it?
It's the string.
And what's the string doing? Do you see that? Can you see it? So this is way slowed down because y is in milliseconds, right? But x is distance down the string. Let's tip back a little more. X is distance down the string, so you see that you're actually seeing the string oscillate, right? X is coming out at us, that's the string. So it's the displacement at all these different locations along the string, and then as time goes by, what does the string do? It goes up and down, right?
Can you change that so we can look down x?
Look down.
So I can kind of see the trough
Gee whiz.
when the string will go down.
I'm just trying to zoom out, and I forgot how to do that. And that's just messing with the... I don't know how to zoom out of my screen. There we go. That's what I wanted to do. So now I'm just going to project that over to the x. So I'm going to project the trace over to the x-axis. Let me try this. Sorry, it needs to go all the way around. Now I need to stop it at just the right time. So this is time going by, and then you're looking at the string. All the points on the string and their displacement, up or down. And then I just projected that onto the xz plane. So that blue is that's the string, and that's just the projection of the trace of the time plane with the surface. Well, that's free. You don't have to pay me for that. Okay, let's see. So what are we going to do? We're going to pick a point here. So what I'm trying to show you is how that surface depicts this multivariable function. That's how this surface shows time being one variable, distance down the string being another variable, and then z being the displacement. That plane moving down then shows time varying, and then the x coordinate or the z coordinate give you the displacement for any x coordinate on the string. So that's just kind of showing how that surface depicts this function. Okay. So okay, so here's a point when what? This is the distance down the string is 80, and the time is 4.75 milliseconds. So I want you to predict, what can you predict about the partial with respect to x and the partial with respect to y at 80, 4.75? What could you predict about the partial with respect to x and the partial with respect to y at 80, 4.75, which is that red point right there? So what could you say? In fact, we could do a prediction for all. So the value of the function, the first partial derivative with respect to x, and so this is now just by looking at the surface and not by looking at the actual formula for the function, just by looking at the surface, what could you say about the value of the function, the first partial with respect to x, and the first partial with respect to y at that point? Tell the person next to you. Everyone's talking to somebody. Predict. What can you say about those three? What could you say about the function value? What can you say about the function value? Without having the formula for the function, and just visually, what can you say about the function value? Anybody? Just Emily? Nick? Chris?
We said that as like y was increasing, z would be going down.
Function value. Just the function value. Is there anything you can say about the function value? Yeah?
You just said it's positive.
It's positive, right? Z is positive. That's the z value. It's above the xy plane. That's all you can say by looking at the... But that's something, right? You can say something. It's positive. It's up above the xy plane. Or this point on the string at this time is above its normal place. All right, what about the partial with respect to x? What's that? So is there anything you can say about the partial with respect to x at that point? I think. Anna? Oh, no, sorry. This Anna. Two Annas. So the partial with respect to x means what? We're going to let x change a little bit, right? So if I let x change a little bit, what happens to z? That's what we're asking. Can you see what happens to z if I let x change a little bit? Does it go up? Does z go up when x increases? It's going down, right? So according to the surface, as x increases, z decreases. Therefore, partial with respect to x? Negative. That's it's a little extreme, but that's the idea. That if you go in the x direction on this surface, you go downhill. X decreases. Does that make sense? Does everyone see that? So this is just horizontal. That's horizontal. That's just saying x is increasing horizontally. Z would go down. That's a horizontal change. dx is changing horizontally, parallel to the x-axis. And when you do that, you head downhill. Z decreases. All right, what about partial with respect to y? So partial with respect to y is this way. That's a horizontal change in y at that point. what will happen to z? Going uphill, right? Aren't we going uphill there? Therefore, partial with respect to y is? Okay, does this make sense to everybody?
Yeah.
The z, the value is positive. The partial with respect to x is negative because z goes down as x increases, as we come out at you. The partial with respect to y is positive because you go up in z as y increases. Is that clear? Okay, so let's look at table of values. So we've looked at the formula function. That's your derivative rules. We've looked at analyzing the surface. Now, what about a table of values? So here's an example. So this is a multivariable function as a table of values, and it's the heat index function. How hot it feels at a certain temperature and humidity. So our x is temperature in degrees Fahrenheit, and y is humidity, and that's a percent. And so then this function, we'll call it capital T, index, capital I, the heat index, x and y, is perceived temperature. Heat index, perceived temperature, the heat index. Okay, so we can use the table of values to make predictions about do that one later. Yeah, so I want to do this one. So let's look at when the temperature is 82 and the humidity is 90. What is the heat index? So that would just be I of 82 comma 90. What is that? 91. Feels slightly, oh no, it feels 9 degrees hotter than it is at a high humidity like that. Okay, so 82 comma 90 feels like 91 degrees Fahrenheit. So how could we figure out the partial of I with respect to t? With respect to t at 8290. So what is that? So we're looking down here, and this means looking at what? Looking at a little change in what? Temperature, right? So a little change in temperature, I'm seeing my little change that I have access to here is 2 degrees on either side, right? I can change temperature 2 degrees here or here, and then I'm going to look at the corresponding what? Change in heat index. What is it there? 7, and here it is 5. 5 from the left, change of 5 this way, change of 7 this way, so we can just call it a day at what? 6, right? So it's like for a change of how much? 2. An estimate here is that the heat index is changing by 6, what? Per change in 2 of temperature. So we can just say approximately equal to what? A change of 6 per change of 2, or? And what are the units on that? Degrees Fahrenheit per. Do they cancel out? No, don't cancel them out because then it's not a rate, right? So this is a rate. It's like how much the perceived temperature changes per actual change in temperature. So those are, you want to leave that as degrees Fahrenheit per degrees Fahrenheit. Okay, so now I want you to estimate the partial of I with respect to, what did I call it? H for humidity. At the same thing, 8290. So figure out the partial of I with respect to H at the same point, 8290. Go, you can work on it together. Okay, awesome. What do you think?
Yeah, it's something like 1.5 degrees Fahrenheit for 5% humidity.
Yeah, so our change in our dependent, what we have to work with is changes of 5, right? So that's the best we have to work with there. And so for a change of 5 in humidity, our change in heat index is, you said?
1.5.
The average of 1 and 2, right? Halfway between 1, this is a change of 1 there and a change of 2 there, so 1.5? Anybody got that? What was that? 0.3? And what's that? Unit. Per percent, right? So, all right, so now I want you to, with your partner, I want you to interpret these two numbers. What does the 3 mean? What does the 0.3 mean? All the details. Practicing partial derivatives. What does the 3 mean? What does the 0.3 mean? Go. How'd you get that? So the change in perceived temperature, the index, is? Three? Negative 0.5. So so if the temperature actually goes down a half, it'll seem like the temperature is going down 1.5, 3 times as much as that. Okay? All right, and what about if the humidity goes up by 2%? Now the humidity goes up by 2%. What can you say? Yeah, Sophia.
The heat index will increase by 2 times 0.3.
So it'll increase by how much?
2 times 0.3, whatever that is. It's the humidity times the 0.6.
Okay. Now tell me what happens. What's going to happen if both of those things happen? The temperature goes down by 0.5 degrees, and the humidity goes up by 2%. What's going to happen? This is what you. You're looking at me going crazy. This is the question you asked last week. Yeah, you said what happens if both of them change? So both of those things are going to change. Yeah, that was your question. What happens if?
That was usual.
What will happen? Yeah, Emily. What's that? And how do you know that? So it'll feel like it's going down because of the change in temperature, but it'll feel like it's going up. How much? So the actual change in the index will be, won't it be just the sum of those two? They're like independent quantities, right? So it'll just be like the sum of those two, which will be? Is that all showing up on the screen? Ah, darn it. So we're going to put it all together, right? So if you were practicing the definition and I actually gave you changes, so that means that the change in the index will be what? The rate was 3, so 3 times the change in temperature. That's showing up now, right? Plus the rate, 0.3 times change in humidity. And that will give us what? Negative 1.5 plus 0.6 equals
Negative 0.9.
negative 0.9. And what's the units on that? Perceived, right? So it will seem like if the temperature goes down 0.5 degree, but the humidity goes up 2%, it'll seem like the temperature is going down close to 1 degree Fahrenheit. Do I have that right? So what happens is then there's something of a rate of change for this proportion of changes. Taking a change in both your one variable and the other variable simultaneously. What's the proportion of those two? What's the proportion of those two changes? Temperature to humidity is about, let's see, so the change in humidity we said was 2, so 2 this way, or sorry, 2 down. And the change in temperature was negative 0.5, so this way. So do you see that proportion of changes is like kind of going like this way in the table? That I'm going down this way 2% for a change this way of negative 0.5%. Do you see that? So what's there's a proportion of changes there. So for that proportion of changes of those two independent variables, there would be like a rate of change kind of for this direction. Do you see that? There'd be a rate of change if you kept those changes of humidity and temperature in proportion. There'd be a rate of change of heat index according to those two changes taken together. So what we're going to transition from is from just these two rates of change in that x and y direction to really infinite number of rates of change according to taking changes in a certain proportion, right? So there's an infinite number of proportions you could take changes in, right? And so in given in any proportion of two changes taken together, there is a rate of change. We'll explore that on Wednesday.